Welcome back. In our last video, we talked about position, velocity, and acceleration. So let's just summarize the equations we came up in those units. So first of all, we defined position as our variable s. We said that our instantaneous velocity was v, and this was equal to our first derivative of our position with respect to time. And then we also defined a as our instantaneous acceleration. And a was equal to the derivative of our velocity with respect to time. So we have two equations of motion that relate velocity to position and acceleration to velocity. And if we rearrange these and substitute them together, we can get a third equation which relates acceleration to velocity and position. So we don't have a function in terms of time anymore. So we could also write a third equation that is acceleration is equal to our velocity times the derivative of velocity with respect to position. And if we rearrange this, we can get it into a different form. Acceleration times the increment in position is equal to velocity times the increment in velocity. So if we have position and we want to go to velocity, we have to differentiate. And if we have velocity and we want to go to acceleration, we have to differentiate again. Likewise, we can go in the opposite direction, and if we have acceleration, we want to go to velocity, we want to go to position, we can integrate. So we can write position going to velocity going to acceleration. Acceleration, we need to differentiate. But if we want to go the other way, start with acceleration. And we want to go to velocity, or if we're at velocity and we want to go to position, we need to integrate those relationships. So let's rewrite these now in our integral forms. The first equation, if we take our acceleration and velocity equation, so let's label these. Let's take equation, let's call it equation 1, 2, and 3. So let's start with equation 1 then. So equation 1 in the integral form, if we rearrange this, we would have velocity times dt is equal to ds. And if we integrate both sides and we solve for that ds term, we can write the integral from s0 to s of ds is equal to our velocity, or the integral from v0 to v of our velocity times dt. And if we do the same process for equation 2, we can say that the integral from v0 to v of dv is equal to the integral from 0 to some time t of our acceleration times dt. And our last equation, we take the integral of both sides. On the left-hand side, we would have the integral from s0 to s of a ds, and that's going to be equal to the integral of v0 to v of v dv. So these are our three equations of motion for a particle in one dimension, both in the differential and integral forms. And using these three equations, or 6 equations, we can solve almost any problem of one-dimensional particle motion. So there's one simplification that we like to do with these equations, and that is assuming that acceleration is constant. There are a lot of problems where the acceleration of motion is under constant acceleration, and that's because a lot of particle motion or object motion is acting under the force of gravity, and gravity is a constant acceleration force acting on everything. So we can simplify the above integration equations if we have acceleration as constant. So we would call our constant acceleration, now we would just say our A term is some constant. So if we're on Earth, we would say our acceleration, our constant acceleration would be equal to g, which is acceleration due to gravity, and that's 9.81 meters per second squared, or we could also write this as 32.2 feet per second squared. So let's look at our first equation. Our equation for position s0 to s ds is equal to integral from 0 to t of v dt. Well, we need to first figure out what is our equation for velocity. So maybe we need to do another step first, and we would look at another equation, and if we can figure out what that equation is for velocity, we can substitute that in here to actually do this integral. So let's skip ahead right now to equation 2. Equation 2 is the integral from v0 to v of dv, which equals the integral from 0 to v of our now constant acceleration term times dt. So if the acceleration term is constant, we can pull that outside of the integral, and we get v minus v0 is equal to ac times t. We can rearrange this into a different form. We could write v is equal to v0 plus constant acceleration times time, which is great. Now we have an equation for our velocity that we can put into this equation here. And if we do that, we can rewrite the right-hand side as the integral from 0 to t of v0 plus act dt. So if we rearrange this whole equation, we'll end up with the equation s is equal to s0 plus v0 times t plus 1/2 constant acceleration term times t. And our last equation, equation 3, was the integral from v0 to v of v times dv, which is equal to the integral of s0 to s, or constant acceleration terms times ds. So if we solve this, we substitute in our equation for velocity, we will get v squared is equal to v0 squared plus 2 times our constant acceleration times our change in position s minus s0. So these are our three equations, 1, 2, 3, our three equations of motion for constant acceleration in one dimension. So we call these our, let's do this in a different color, our one-dimensional equations of motion for constant acceleration. So it's very important that we remember that these equations are only valid when we have constant acceleration. If acceleration is changing with respect to time, then we can't integrate equation 2 like we did and use that expression for velocity in the other two expressions, and our integrals would be different. So we would have to use the general forms of our equations for the condition where acceleration isn't constant. Let's do an example now. In this example, we have a particle traveling along a straight line to the right with a velocity v is equal to 4t minus 3t squared meters per second, where t is in seconds. It also tells us that s is equal to 0 when t is equal to 0, and the question is asking us to find the position and acceleration of the particle when t is equal to 4 seconds. So we're given a function for velocity, we're given some initial conditions s0 and t is equal to 0, and it's asking us to find position and acceleration when the particle when t is equal to 4 seconds, so after 4 seconds. So we can start by finding the acceleration, and we can write the acceleration from our equations before is equal to the derivative of velocity with respect to time. So the derivative with respect to time of 4t minus 3t squared, which is equal to 4 minus 6t. It's asking us to find the acceleration at a time t is equal to 4 seconds. So if we substitute 4 seconds into here, so at 4 seconds, or let's just write when t is equal to 4, we get acceleration is equal to 4 minus 6 times 4, which is minus 20. So next we need to find the position of the particle at t is equal to 4 seconds. So to do this, we can use our integral form of our equation. And notice we can't actually use our constant acceleration because we just found out that acceleration is a function of time right here. So it is not constant. So we have to use our general form equations, and we have to do the integral of this equation for velocity. So the equation we can use is the equation that relates position and velocity, and that is the integral from s0 to s. ds is equal to the integral from 0 to t of our velocity function times dt. So we can write this as s0 is just 0, so the integral on the left-hand side is just s, and that is equal to the integral from 0 to t of our velocity function, 4t minus 3t squared dt. And this is equal to 4t squared over 2 minus 3t cubed over 3, all evaluated from 0 to t, and we care about when t is equal to 4 seconds, so evaluate from 0 to 4. And if we do this, we get our answer to be minus 32 meters. So our position after time is equal to 4 seconds is 32 meters in the negative direction.